Alternating series are a type of series, and when you see an alternating series, there's a specific test you can apply to it that's pretty simple. And so as soon as you see an alternating series, your eyes should light up and you say, okay, this is going to be pretty easy. For many reasons, alternating series are your good friends when you're studying infinite series. To recap what we had before, when we're faced with a series in this chapter, we ask two questions. One, does the series converge? And two, if it does converge, is there a way to figure out the sum? What the alternating series test will let you do is answer the first question for a series that alternates. It has nothing to do with the second question, and generally when we have an alternating series, we cannot find the sum, so that's not involved in this video. All right, so first, what alternates in an alternating series? So if you want to pause the video and answer questions as we go along, and I'll say pause when that's a good thing to do. So what alternates is the sign, the plus and minus sign. So here's some examples. Take a look at these. Here they are written in Sigma notation. There's one down here. And then this is interesting. This is in the homework and is a common problem that comes up on tests and in books to see if you understand what's going on. If you go through this and plug in 0 for n, and then 1, and then 2, and then 3, you'll see that what the top does is it's 1, and then -1, and then 1, and then -1, which creates the same thing this does. So this is a sort of hidden way of creating an alternating series. All right, here's the test. And remember, this only works if the series is alternating. The signs have to go plus, minus, or minus, plus, minus, plus. All right, so here it is in words, and then in part B, it's in math language. So this will say the same thing twice. Two conditions have to be met. The first condition is it's an important one and a very common one that you'll deal with, I would say 95% of the time. So what's in black here is the one to really know. So if you're in a hurry and you can't learn everything perfectly, you absolutely want to know what's in black. And if you really need to, you could ignore what's in blue. This comes up maybe one time out of 20. So first, all the series has to do is pass the nth term test. There is a second condition, which as I said comes up rarely, is important rarely, but we'll say it here. It has to pass the nth term test and the terms have to shrink steadily. If those two things are true, then you can be guaranteed that the series converges. What if they're not true? Well, if this one is false, if the series doesn't pass the nth term test, that's from a previous video and previous homework. We know automatically the series diverges. This is a test we can always do first on our series, and if the series fails this test, we don't have to go any further. So the series has to pass the nth term test, and with an alternating series, 95% of the time, the series converges and you're done. However, there's this second thing. The terms have to shrink steadily, and I'll explain what that means in a minute. If a series passes this one and fails this one, it tells you nothing, but we'll come back to that later. All right, here it is in math terms. Here's how you write an alternating series. You put the alternating part in this. And then to make this an alternating series, that means this has to be positive. So we understand that we're putting the alternation here with all of the a sub n's positive. That's how we write an alternating series in general. So for that kind of series, then these two things have to be true. Again, in black ink, pass the nth term test, written there in math language, and in blue ink, the less important criterion, the shrinking steadily. What that means is that each term is smaller than the one before it, or it can be equal. Now, it doesn't have to be true right away. The terms can start getting bigger for a while, as long as eventually, past some point, they all start shrinking steadily, meaning each one is never bigger than the one before. Right? If those two things are true, they're in math language, then we can be guaranteed that the alternating series converges. Right? There's commonly a confusion at this part. You may want to pause the video and just think this all over and what this means. Go through it several times. Make sure you understand what these means and see if it makes sense to you or if it doesn't. And then turn to this. For a lot of people first running into this, they'll say, wait, isn't that just saying the same thing twice? How can a series pass the nth term test? How can the limit be 0 without the terms shrinking steadily? Or if the terms do shrink steadily, doesn't the limit have to be 0? The answer is absolutely not. These are two different things. So here's some counterexamples to show that. In the blue one here, we have terms that are shrinking steadily. Every term is smaller than the one before it. If you ignore the signs, we're talking about absolute value, the a sub n part of the term. 2.1, 2.01, 2.01. every term is smaller than the one before, so it passes the blue requirement. But are these terms shrinking to 0? No. What are they shrinking to? They're shrinking to the number 2. So this example passes the second part, the blue part, and fails the black part. And then this example here, look at the terms, 100 minus 10, plus 50 minus a little bit of 5, plus a lot of 25 minus a little bit of 2.5. These terms technically do pass the nth term test. They technically do approach 0. 100, 50, 25, they're getting smaller and smaller and smaller, and you can confine them within a space that gets smaller and smaller and smaller. So technically, these terms do have a limit of 0. But is every term smaller than the one that came before in absolute value? And the answer is no. 50 is bigger than 10 and so forth. So this is an example of a series that passes the black part and fails the blue part. All right? Here are some examples. You may want to pause the video and try all of them yourself. Do the series pass the alternating series test and converge, or did they fail it? All right, let's go through these. Now, I want to point out this is always given as the first example, or it should be when you learn about alternating series, because you know that if it's not alternating, this series 1 over n, that's the harmonic series, and that's very famous because when you learn infinite series, it's a very useful series because the terms clearly shrink. Each term is smaller than the one before, but this series diverges. And we can do that by seeing that it's a p-series, p equals 1, it diverges. It's just like the integral of 1 over x. The integral is natural log, and that is a function that increases without bounds. So the improper integral of this diverges. The series itself diverges if it's non-alternating, if it's all positive. If this is all positive, the series diverges. But now let's consider it alternating. There it is. Does it pass both tests? The terms shrink to 0, yes. As n gets bigger and bigger and bigger, this approaches 0. Okay, is each term smaller than the one before in absolute value? Yes. So this series passes the alternating series test, and therefore it converges. All right, let's look at this one. This one's even worse than that one if it's all positive. This one has a p equal 1/2, so it's a p series with p less than 1. Definitely diverges. If you did the improper integral of this, definitely diverges, but it's alternating now. So let's apply the alternating series test. Does it pass the nth term test? Are the terms approaching 0 as n gets bigger and bigger? Yep. And is each term smaller than the one before? Yep. So this passes, and therefore it converges. All right, now let's try this one. I wrote out the series, and you can see, oh yeah, the terms are shrinking. They're getting smaller. Okay, each term is smaller than the one before, but do the terms converge to 0? And here, this will take you back to some of the nth term divergence test homework. How do you test this thing, that term, that formula, to see if it approaches 0 as n gets bigger and bigger and bigger? Well, you treat it as a limit, and this is one of the reasons you learn so much about limits when you study calculus, so you can analyze series, because series are so useful, one of the most useful parts of math ever invented. So let's look at this and think about, you can pause the video, think about how you would do this. Right? Well, as n gets bigger and bigger and bigger, only the term with the biggest exponent dominates on top, so that doesn't matter, and dominates on the bottom. Now we have 3n over 4n. Simplify, n over n makes a 1, and this, the terms here, the individual terms, you can't really see it looking at this, but the individual terms get closer and closer to 3/4, not 0. So this fails the nth term test. And you wouldn't even have to do the alternating series test. Even if you didn't know about the test that was on the previous board, you could still say this diverged because it fails the nth term test. So it diverges. All right, let's try a trickier one, the kind of problem they like to put in calculus homework assignments, because the relationships are kind of hidden in all of this. So let's see, I wrote it out just by plugging in some numbers, and yes, it alternates, and it looks like the terms here, they're equal, but then they start shrinking. Okay, that looks good. But let's rearrange it so we can see the pattern it has. So it's not standard to write alternating series like this, so let's make it, force it into standard alternating series form. Take that, what's in the bottom, and write it as -1 times +2 to the n minus 1. All right, and then this is -1 to the n minus 1 times 2 to the n minus 1. If you think about it a while, this is exactly like putting negative 1 to the n minus 1 in the numerator. It has exactly the same value, so we'll put it up there so it has that standard form, times n, and then this is a two-part exponent, so write it like two things multiply together. 2 to the n times 2 to the negative 1. Right? 2 to the n times 2 to the negative 1, add the exponents here and you would get that. And finally, let's rearrange the whole thing. So we put it in the form that we're familiar with. This 2 to the negative 1 is like having a 2 on top. We can write that out front, just like factoring out a constant to the front of an integral. Then we don't have to think about it. It has no effect on whether it converges or diverges. Then we write the alternating kind of operator here. That makes the series alternate. And then look what's left. N over 2 to the n. And now what's nice about this is we can focus just on this. It's an alternating series. We can ignore that. That has no effect on converging or diverging. It's an alternating series. Now we're just looking at this and asking our questions. Does this pass the nth term test? And is each term smaller than the one before? All right, let's see if it passes the nth term test. Now you could do some kind of limit on this, and I hope L'Hopital would immediately spring to mind. And if it doesn't, replace each n with an x and do it as a limit in x. That'll often trigger your mind to think of the correct technique. But we learned earlier that we could use growth rates, and what you have on top is a power function, and what you have on the bottom is an exponential. So what you have on top is a slower function, and what you have on the bottom is a faster function. We have those 4 different families of functions. Go back to a previous video on growth rates. Since it's slower or faster, we can just go, we don't have to do any work. We automatically know that this limit is 0, so therefore it passes the nth term test. And you can do a little bit more work, which I'm not going to do on the board. You can see it in my solutions. But it's easy to see from writing out a few terms that each term is smaller than the one before. So therefore, this passes the alternating series test. Therefore, it converges. Right? And then finally, if all you want to do is problems, it's fine to stop here. Sorry about that. But if you want to understand why the test works, then you should watch the rest of the video. And this can help you understand especially why you have to have that second requirement, the one I keep writing in blue. So first, why does this test work? Think of each positive term as a climb up, as putting a ladder up, and we write those in black. And each negative term is a loss of elevation. And then look what that does for the partial sums. So what I've done is write out a sample alternating series here, the alternating harmonic series. Then I represented each term with an arrow, up a 1, down a half, and so forth. And now we're going to write those out on a graph. This is numbers, and this is the n. So n equals 1, n equals 2, and so forth. So first we start off, if you only took one term of this series, you go up to there, and the first partial sum, S1, would be 1. Now, if you took the first 2 terms, you'd go up 1, and then you'd go down a half. You'd take away a half. So you'd add 1 and take away a half. And that would create the second partial sum. In other words, if you took the first 2 terms, the second partial sum would be 0.5. All right, now let's take 3 terms. So we add in the 1/3. So that's about maybe this far. All right, and that partial sum there is 0.83. So that's the third partial sum. That's not a 5, that's an S for sum. Okay, you know what comes next. In fact, you may want to pause and write this out, write the rest of it out yourself and see if you can draw a conclusion from it. Take away a quarter. Okay, and that gives us the next partial sum is 0.58. That's S4. And we'll just do one more. Add back a 5th. Okay, and that gives us the next partial sum, which is 0.78. So look what the partial sums are doing. First, we're up to here, then here, then here, and then here. They keep wobbling back and forth, but the wobble gets smaller and smaller and smaller. So we know that the partial sums are getting trapped in a smaller and smaller area. And you can never calculate the actual sum of the series. It doesn't have a sum that's non-repeating, non-terminating, or non-terminating. Doesn't have that kind of sum. But the more terms we take, the more we can confine it and get a better and better estimate. So you can see why an alternating series will converge as long as it meets both criteria, that the terms shrink towards zero and each term is smaller than the one before. You go up, take away less, take away less, add less, and you get this wobbling effect. And so the sums, as you take them, S1, S2, S3, S4, S4, they keep getting confined to smaller and smaller spaces. So the sequence of partial sums, 1, 0.5, 0.83, 0.58, 0.78, it has a limit. It's clear, we don't know the number, we can't express it as a single number, but it clearly has a limit. It's confined in smaller and smaller spaces as we take more and more terms. So that answers the question why it works. And then finally, the most esoteric thing in this section is, why do you have that blue requirement? Why do the terms have to shrink steadily? Why does each term have to be smaller than the one before, or at least not bigger? Why can't the terms just shrink to zero? And I'm not going to do a formal proof, but an example I think will help you understand why. So look at this example. The ultimate limit of these terms is zero, because both the blue and the red terms are getting smaller and smaller and smaller. So the terms are shrinking closer and closer to zero. But each term is not smaller than the one before in absolute value. 50 is bigger than 10. So let's see what happens if we do the same action on this series that we did on here. Okay, so we write the first term, and you may want to pause the video and try this on your own so you can see where it's going, and it'll just jump out at you why the series might diverge if it fails that second test, if it fails the blue test. Remember, this series fails the second test, the rare one, the test that comes up 5% of the time, the one I keep writing in blue. In this test, the terms don't shrink, or in this series, the terms do not shrink steadily, but they do approach zero overall. So there we go, up 100, down just a little bit, down just 10. And now we go up more than we just went down. So we go up 50. Okay? Then we go down just a little bit, which on here 5 is going to be just like that. Okay? Then we go up 25, much more than we just went down. Then we go down almost a dot, and then we go up more. So look where the partial sums would be. The first one would be at 100. The second one would be at 90, which would be there. The third one would be at 140, right? And then take away a little, then add a lot, take away a little, add a lot. And what you get is that kind of shape for the partial sums. Instead of a wobbling back and forth that gets smaller and smaller and smaller, you get this climbing thing that's concave down. It will be concave down, but it climbs. So what does this tell you? What if it passes the nth term test, passes the test I have in black ink, the first part, but fails the part in blue test? What does it tell you? Well, look at this kind of shape. Does this kind of shape ever converge? Yes, it does. Like if you have 1 minus 1 over e to the x, that can converge. Okay? Or does it ever diverge? Yes, like square root of x. That shape diverges. So this, if it fails the blue part, if it fails the second part of the alternating series test, it tells us nothing. So if it passes the first part and the terms pass the nth term test, but it fails the second part, that's the case, that's the only case where the alternating series test tells you nothing.